As Dwight said, experience is the best teacher, which is what lab is all about. Let's go through the objectives for the VLE experiment. The first objective is to collect experimental data in the infinite dilution limit for binary systems of acetone, 2-propanol, and methanol, and then use activity coefficient models to predict their VLE behavior. The second objective is to predict the behavior of a ternary system of acetone, 2-propanol, and methanol using the data collected from objective number 1. The third objective is based off of the design problem, which we'll go over later in this video, but it is to design an isothermal flash process for the partial removal of acetone from a methanol and 2-propanol mixture.
Vapor-liquid equilibrium is the thermodynamic equilibrium between a mixture's liquid and vapor phases. VLE is achieved when thermal and mechanical equilibrium is present and the partial molar Gibbs free energy of all species is the same for both the liquid and vapor phase. Those three requirements for thermodynamic equilibrium is presented as follows. The third criteria for partial molar Gibbs free energy can also be expressed using the respective liquid and vapor phase fugacities. For the calculations in this laboratory, we will be using the vapor and liquid fugacity expressions. Here is the expression for the vapor phase fugacity. It is the product of the vapor mole fraction, the total pressure, and the fugacity coefficient for component I. Here is the expression for the liquid phase mixture fugacity. It is the product of the liquid mole fraction of component I, gamma the activity coefficient, V the fugacity coefficient, the vapor pressure of component I, and the Poynting correction factor. To solve for the fugacity coefficients, we use the principle of corresponding states, which generalizes that the properties of a gas are dependent on intermolecular forces and are related to the critical properties of the gas. When two fluids have the same values of reduced temperature and pressure, they are said to be in corresponding states. To calculate the reduced temperature and pressure, we use literature data from Perry's Chemical Engineer's Handbook and 1 atm per pressure because the system operates at atmospheric pressure. The results from those calculations are presented here. Normally, the fugacity coefficients can be read off of figure 7.1 in Sandler's textbook, but due to our rangers, the following equation from chapter 7 is used. Here you can see that as PR goes to 0, our entire integral goes to 0. The fugacity coefficient is ultimately approximated to 1. Therefore, the vapor phase fugacity can be simplified to just the vapor mole fraction times the total pressure. Now examining the liquid phase mixture fugacity, we will simplify the Poynting pressure correction. Examining the integral, the partial molar volume of species I, R the gas constant, and T the temperature can be taken out of the integral because they are constants. Evaluating the integral, the Poynting pressure correction becomes this. For our system, Pi vape is equal to P because our system is open to the atmosphere and boils at atmospheric pressure. Therefore, P minus Pi vape equals 0, so our Poynting correction becomes the exponent of 0, which equals 1. Returning to our original expression for liquid phase fugacity, and using 1 for our fugacity coefficient and 1 for our Poynting correction factor, our liquid phase mixture fugacity is simplified as follows. Using the requirements for vapor-liquid equilibrium and our simplifications for both the vapor and liquid phase fugacity expressions, we have our final equation, which is used in this lab to predict VLE behavior.
Guys, I have no idea what fugacity is. You know what this means.
Come in.
Hi, Dr. Skirto.
Hi, Tammy. How are you?
Good. I know it's been a year since I've taken Thermo 2, but I was wondering if you could just explain to me what fugacity was.
Okay, well, please take a seat. So, fugacity stems from the combined first and last of thermodynamics, whereby we get up criteria in order to figure out what do we need to specify in order to have phase equilibria. So, two or more phases that can coexist in equilibrium. And they start from the combined first and second law, but what we get from the first and second law are really chemical potentials, which we could use, and our physical chemistry friends use it. But what we find is that the chemical potential has some difficult to compute mathematical forms, like when you have a dilute solution, it goes to negative infinity. And so what G.N. Lewis, a physical chemist, was invented this concept of fugacity, which has the same kind of meaning or same kind of use as chemical potential, in that chemical potentials in each phase have to be equal, or mixture chemical potentials of each phase of each species. But now we can construct this term fugacity, which combines chemical potential, is really just the departure function of chemical potential, in a much nicer mathematical form, in that when we go to dilute solutions or low pressure, instead of going to negative infinity, it goes to the pressure of interest. And so when we start our phase equilibria, like vapor-liquid equilibrium, we have the fact that the fugacity now, the mixture fugacity of each species and each phase are now going to be equal to each other in a nice mathematical form that doesn't have some difficult to compute pitfalls or anything like that.
That makes a lot more sense now.
Moving on with the theory, let's talk about activity coefficient models. They were developed as a means to calculate activity coefficients, which are correction factors for non-ideality in mixtures due to their intermolecular interactions. And they show up here in the fugacity expression, so it's important to know how to calculate them. Two different activity coefficient models were used in this experiment. The first model, the Van Laar, assumes a completely random mixture where the distribution of molecules is consistent throughout. This equation was derived from the van der Waals equation and is used for liquid mixtures where the molecules of the components have similar shape and interactions. The equations for the Van Laar model are shown here. In this lab, we will be operating in the infinite dilution limit, meaning that the amount of solute in the system, X2, is much smaller than the amount of solvent, X1. Taking the Van Laar activity coefficient model at these infinite dilution limits, the following equations result. These will be useful in calculating the Van Laar parameters later in this video. The second activity coefficient model is Wilson's model, which was the first to consider the concept of local composition. Local composition theory assumes that the mixture is non-random and local mole fractions will deviate from overall mole fractions due to stronger or weaker molecular interactions from surrounding or nearby molecular groups. Wilson's model can also be taken at infinite dilution limits, resulting in the following equations. These equations will be used to solve for the Wilson parameters later in this video. In order to solve for the infinite dilution activity coefficient itself, we can use this equation, which is derived from the vapor and liquid mixture expression fugacities, where Pj vape is the vapor pressure of the solvent and can be solved for using Antoine's equation shown here. The next term in the equation is the derivative of the vapor pressure with respect to temperature, which is shown here. The dt over dx term at infinite dilution limits is determined from the experimental data in this lab. Finally, Pi vape is equal to the vapor pressure of the solute and can be again calculated by Antoine's equation.
Fire! Oh, fire! Oh my goodness! What's the procedure? What do we do, people?
The bones are dead.
Oh, how did that happen?
For this lab, proper PPE should be worn and includes long pants, closed-toed shoes, a lab coat, nitrile gloves, and safety glasses. One of the hazards in this experiment was the chemicals being used. It is important to consult the MSDS sheets for potential side effects in first aid procedures. In case chemical exposure does happen, note the location of the safety shower and eye wash station. It is also important to know where the fire extinguisher is located. For this lab, temperatures greater than 60 degrees Celsius were considered hot and treated with caution. When emptying components from the ebullirometer, make sure that the mantle temperature is less than 50 degrees Celsius. Be cautious of any tripping hazards in the lab and clean up any spills immediately to avoid slips. In this lab, the syringe is posed as a sharps hazard due to the scalpel tip. These hazards were minimized by capping the syringe after use and carrying it tip side up.
In this lab experiment, you will be working with 4 ebullirometers that will run simultaneously to collect data for the different solute-solvent combinations. Ebullirometers are instruments that have been designed specifically to accurately measure the boiling point of liquids by measuring the temperature of vapor-liquid equilibrium. The system is open to the atmosphere through the condenser so that operation will be run at constant pressure. In the condenser, the vapor fractions that rise up are condensed to prevent mass loss. The condensate will eventually return back to the boiler. You will also see a temperature probe above the condenser. The temperature recorded here is to ensure that the condenser is properly functioning and that hot vapors are not being released into the lab. Next, you see the injection port. This is where the solvent and solute are injected using syringes. Moving down, you'll see the thermal well and the Cottrell arms. It is in this region that the vapor-liquid equilibrium occurs. The resistive temperature detector sits inside the thermal well. That device will collect the temperature of the vapor-liquid system in lab view. Once operation begins, the rising vapor phase will move up the Cottrell pumps. The vapor phase contains small drops of liquid creating a VLE mixture. Separation occurs when the mixture hits the thermal well, where gravity drives the liquid phase down the boiler and the vapor phase will continue to rise further to the condenser. The boiler is at the bottom of the ebullirometer. Each of the boilers are supplied with a separate heat source that will bring the temperature of the injected mixture to a boil. The temperature of the heater is indicated on this display along with the emergency stop button. The display for the resistive temperature detector and the pressure reading from the barometer is located above the laptop.
Open up the LabVIEW software from the desktop. Turn on both condensers if they aren't already on. Make sure that the stopcock is closed before any liquids are added. Before starting this experiment, it is essential to correctly label your materials. Label each syringe and container adequately to omit possibility of cross-contamination. Pour the stock solvent into a smaller container. Remember, with the chemicals that are present in this experiment, it is important to recap both containers because these solvents quickly evaporate. Next, draw around 50 milliliters of the solvent out of the smaller container using a 60 milliliter syringe. After the desired amount is attained, recap the syringe. Next, record the mass of the solvent-filled syringe. Inject the solvent through the injection port by gently piercing the septum. Keep in mind there is glassware around the port, so limited force should be used. When finished, recap the syringe. Mass the empty syringe in order to find the amount of solvent injected into the ebullirometer. In order to start the LabVIEW software, press Run in the upper left-hand corner of the screen. The file should be saved as a text file to easily be able to later paste it into Microsoft Excel. Once the LabVIEW software is running and your solvent is charged to at least 50 milliliters, the heater may be turned on. If you have not injected your solvent, do not turn on the heater. Once the boiling solvent has reached its equilibrium temperature, the solute can be measured using a 2.5 milliliter syringe. Once again, recap the syringe. Next, mass the solute-filled syringe. Inject the solute into the injection port. This process will be repeated and a total of 5 solute injections should be made. Take the mass of the empty syringe in order to see the amount of solute that was put in the ebullirometer. Once all of the injections are complete, tare an empty beaker on the scale. This beaker will be used to measure the amount of liquid in the ebullirometer. Once the RTD reads below 50 degrees Celsius, open the stopcock and release the liquid. Record the mass of the liquid, then dump it in the waste container. When you are finished, make sure that the lab station is clean and ready for the next group to use.
Although 3 different solute-solvent pairs were explored in this lab, for the sake of data analysis, we're just going to look at the system of 2-propanol and acetone. This figure represents the experimental data collected in the lab for the system of 2-propanol in acetone, meaning that 2-propanol was the solute in the solvent acetone. As you can see, with each solute addition indicated by the arrows, the temperature of the system increases overall. This is because the boiling point of the solute, 2-propanol, is higher than the boiling point of acetone. Figure 2 is the experimental data collected in lab for the opposite system, meaning that acetone is now the solute in the solvent 2-propanol. Now, with each solute addition, the overall equilibrium temperature is decreasing because the boiling point of the solute is now lower than the boiling point of the solvent. With the experimental data, a plot like figure 3 can be created with 6 points, 1 point for the pure solvent and 5 points for each of the solvent additions. In each case, the total mole fraction of the solute in the system after the addition is plotted versus the equilibrium temperature observed from the experimental data. The plot shown here is for 2-propanol in acetone, and this plot is for acetone in 2-propanol. Now, why are these plots important? It's because it relates back to the expression for the infinite dilution activity coefficient explored earlier in this video. The b term in the polynomial line of best fit for this graph is equal to the dt over dx term denoted here in this equation. Because the other parameters in this equation are known through Antoine's equation, the infinite dilution activity coefficient can be calculated. From the infinite dilution activity coefficients, both the Van Laar parameters and the Wilson parameters can be calculated. Finally, once the Van Laar and Wilson parameters are known, these models can be used to compute the activity coefficients for a known liquid composition, x1 and x2. Looking back at the fugacity expression, we now know xi, the composition of the liquid, from the masses recorded of the solute and solvent during the experiment. We know gamma I from the activity coefficient models, we know the vapor pressures from the Antoine's correlations, and we know the pressure of the system because it's open to the atmosphere. This leaves us with 2 unknowns, temperature and vapor composition, which can be solved for using a bubble point temperature calculation. The results of this calculation can be represented in a TXY diagram like the one shown here for the 2-propanol and acetone system when the Van Laar parameters were used to calculate the activity coefficients. From the TXY diagram, we can see both the bubble point and dew point curves in between which vapor-liquid equilibrium is occurring. The literature data is also plotted here alongside the experimental data for comparison. The results of the bubble point temperature calculations can also be represented in an XY diagram like the one shown here for the 2-propanol and acetone system with the Van Laar parameters. Again, the literature values are plotted side by side for comparison. Figure 7 is the TXY diagram that results from the bubble point temperature calculations of 2-propanol and acetone, this time using the Wilson parameters. This graph looks extremely similar to the one using Van Laar parameters because both fit the literature data rather well. However, calculations between the percent deviation of the literature and model data reveal that the Wilson fits the data slightly better and was therefore used in Aspen calculations.
For this lab, we were tasked with solving the following problem. A pharmaceutical company accidentally contaminated their supply of 100 drums of acetone with 10 drums of waste solvent, 40 weight percent methanol and 60 weight percent 2-propanol, which is used in the purification of a highly profitable drug. As a result of this contamination, the company will be forced to shut down production for 2 weeks until more acetone can be received, resulting in large revenue losses. In an attempt to keep operations running, the company is looking to quickly design a flash process that can remove acetone at 95 weight percent purity from the methanol and 2-propanol mixture. When examining this system, the Wilson model was chosen because of its fit to the experimental data gathered for the binary systems in lab. Aspen was used to generate a ternary diagram, seen on this slide, for acetone, methanol, and 2-propanol. Aspen was also used to identify the known azeotrope, which occurs at a temperature of 55.24 degrees Celsius and a composition of 77.7% acetone and 22.3% methanol. Knowing this information, the next step was to design the separation. In order to reach the desired 95% purity of acetone, 2 isothermal flash units were utilized. The operating conditions for each flash unit was determined using iterations and a sensitivity analysis. Using only one flash unit operating at 34.8 degrees Celsius and 0.45 bar, 1,572 kilograms per hour of vapor was recovered with a purity of 93.7 weight%. Adding in a second flash unit in series, operating at 30.91 degrees Celsius and 0.39 bar, 207 kilograms per hour of vapor was recovered with 95.03 weight% purity of acetone. Although we modeled our system using 2 isothermal flash units, the system could also be done using 1 flash unit, which would result in a higher recovery than 2.
Here are some tips to make the report writing process go as smoothly as possible. First, it is important to delegate specific tasks for each member so that everyone knows what part of the report they're responsible for. Also, make sure you are coordinating with your group members throughout the writing process because it is inevitable that you will have questions about your part that your group members may be able to answer. Don't be afraid to ask for help from your professor as you're writing your report. Time management is arguably the most important skill that you need to develop a quality lab report. These reports can take many hours to complete, so it is important to not wait until the last minute to do your work. Once your lab report is complete, it's important to review your work to make sure you have a cohesive piece of writing. Make sure that you print out a copy of the report for every group member and have every single person go through and mark up everything that's wrong with the report. This way, you'll be sure to not miss any mistakes. Alright, that's it. Follow these tips and you'll be sure to be looking like this when you get your report back.
We did it!